Welcome back to this session. Our second speaker is Timo Seppäläinen from University of Wisconsin. And to introduce him briefly, he got a PhD from University of Minnesota in 1991. And he's currently serving as the editor of Variational probability. And he is a winner of 2000 prize of the Aug18Mon Plus, right? And he has been fellow of IMS since 2010, and he was a 2014 IMS medallion lecturer. And his research is mainly on probability theory in general and random walks, interacting particle systems, and large division theory in particular. So, Dr. Timo Seppäläinen, please.
Thank you for the introduction, and thanks to all of you for showing up, since there are two very interesting competing lectures at the same time. And obviously a great big thanks to the organizing committee for choosing me, giving me this great honor, and also for the wonderful organization of this meeting. It's truly been a pleasure to be here. All right, so that's my topic, variational formulas for directed polymer percolation models. So let me start with a quick overview of what's to come. So the topic is, these are models of random paths in random environments, and there are two kinds, directed percolation and directed polymers. And the novelty I'll show you are certain variational formulas for laws of large numbers limits that arise naturally in these models. And when we look for minimizers for these variational formulas, we encounter something called Aug18Mon functions, which is a notion familiar from geometry, where it's been used to study geodesics, and this notion was brought into probability 20 years ago by Chuck Newman. And there's a bigger context to my talk, which you may have already seen twice. This morning in Alexei Borodin's plenary lecture, and 2 days ago in Ivan Corwin's talk in the math physics section, this KPZ universality class arose. So these models that I'm talking about, they are expected to lie in this universality class. So that's the bigger context. And as you saw in those previous talks, universality is still but a dream, and our window into the properties of this universality class is this small collection of exactly solvable models. So towards the end of my talk, I'm going to switch gears and go from the general model to a particular exactly solvable model. But to begin, and to put us in the right frame of mind, let me just remind us of random walk and the two most basic big theorems of probability. So for random walk, we take IID random variables, and let me assume they have a finite mean and the variance. And random walk is, of course, what we get when we add up these random variables. So we get this position Sn indexed by time n. And the two big results are, of course, first of all, the law of large numbers that tells us the long-term velocity of random walk, and then the central limit theorem that tells us about the fluctuations. So I want to highlight two features of these two results to contrast with what comes next. So the first feature is that because of the linearity of the random walk, the identity of this law of large numbers limit is immediately given to us. There's no mystery about it. And the second feature is the universality, which Alexei so convincingly already demonstrated to us this morning. So the universality here is contained in this exponent 1/2 and the Gaussian limit, which are shared by all random walks with finite second moment. Okay, so let's proceed then to the actual object of study, directed percolation. So here's a piece of the two-dimensional integer lattice, and what I want to do is attach a random number, a random weight, to each point on the lattice. So call those omega x's. And altogether, they make up what we call a random environment, or a random medium. And I'm assuming that the random variables omega x are all independent and identically distributed. And the geometric feature I want to think of are paths on this lattice. restricted so that they take only nearest neighbor steps, and every step is to the right or up. So there's that red path, an example. And each path has a weight, which is simply the total accumulated weight along the path, right? So I sum over the points x along the path, and what I sum up are these weights omega x. So this setting will be constant throughout the talk. I'll look at it from a slightly different angles now and then, but the picture is the same for the duration of the talk. Now what I want to do next is imagine two fixed points on the lattice, say a point U and a point V, and I want to think of all the ways of building a path from U to V, and take the one with the maximal weight. So that's this random variable G of U and V. So this is the so-called last passage percolation. Last passage because the slowest path wins. If you want to think of these weights omega x as passage times, the time it takes to get through that particular point on the lattice. So where does a model like this arise? In a number of places, but in particular in queuing theory. So if you imagine that the two axes of this picture index service stations on the one hand and customers on the other hand, and these omega x's denote the time it takes for a particular customer to get through a particular service station, then it turns out that this quantity G of U and V calculates the total time it takes for a customer to get through a whole series of service stations. So there's a very firm sort of applied story behind this. But I'm afraid I don't have time to really explore that fully. But let's ask the natural questions next. As often in probability, we want to understand what happens in large scale. Once we lay down some microscopic random rules, we want to understand the big picture. So here the natural question is, let's anchor one of the starting points of the path at the origin, and let the other one, the x here, vary. And let's imagine taking x large, far, far away. How do we expect this last passage time g0x to behave? So now here I want to make a contrast with that random walk situation. We no longer have linearity, because this maximum here makes things non-linear in this x variable. But we still have something that's almost as good, namely we have superadditivity. And the reason is quite simple, right? If I want to go from 0 to y and find the maximal path, one possible strategy is to stop at x along the way, but since it's only one of the many strategies, I get an inequality rather than an equality, right? Hence it's superadditivity. And of course, the younger guys who are really sharp there will maybe realizing already that this is not exactly true now because the weight at x is counted twice. But let's not worry about that. For example, I could change my definition of G0x a little bit and ignore the first weight of the path or something like that to make it accurate. So these kinds of problems arose in the 50s and 60s, and they led to a fantastic development in probability that has influenced our work ever since, so-called Savardi-Vergadic theory. Here are some of the protagonists, Hammersley and Kingman in the UK, and then a little bit later, Keston and Liggett in the US. And the net result of that development was that under suitable hypotheses, this kind of a situation is good enough for an ergodic limit. So here is an immediate application of that theory, which is then the starting point really for my talk. So let's make a little moment assumption on the weights. This is more than is really needed, but later on I will need this, so let's make it right away. And the basic result is that if I look at the last passage times on the scale n and divide by n, then there is a deterministic law of large numbers limit. So I'm indexing these limits here now by a vector xi from the first quadrant of the plane, which gives me the velocity, the direction I'm going into. So I'm looking at last passage time from the origin to n times xi, dividing by n, taking the limit, and in the limit there is a deterministic function of xi. All right, so this sets the stage for everything that follows. So can I answer any question at this moment about anything you've seen so far? So the theme now will be to try to say something about this limit function g. And you may wonder what are the subscripts and the superscripts here. PP here is point to point. There will be a contrast with something called point to line a little later. It just means that I'm taking last passage times from one point to another point. And the superscript infinity there means zero temperature. You will also understand that a little bit later, just in a couple slides. All right. But what can we say about this limit? Well, the ergodic theory itself is not very helpful here. It just gives an asymptotic representation, which is almost no better than the limit itself. If I restrict xc to an integer point, then this is a true fact here. Some soft properties of this limiting function are easy, like continuity, concavity, homogeneity. But then if you ask about differentiability, already that's impossibly hard. Right? Nobody knows how to prove that. So the quest for this talk is now to ask, can I find any other characterization of this limiting function except this sort of asymptotic limiting type? And the way I'm going to approach this is perhaps a little bit surprising. I'm going to add more noise to the model. So the last passage formulation, this maximum over weights, focuses on the best possible path. If the weights have a continuous distribution, it's unique almost, sure. But let's relax the rules a little bit and give every path a chance to be the special one. But with probabilities that depend on those weights, with bigger probability for higher weight. So this takes us to a model that arose in the stat physics literature in 1985 called the directed polymer model. So here are the ingredients. The same weight of a path as before, some of the weights along the path. But now each path has a chance of being chosen. So the probability of a path is now proportional to the exponential of the weight. Beta is just a constant I'm going to throw in for good measure, actually an important constant. Its physical meaning is that of inverse temperature. And Z is simply a factor that normalizes this to a probability. But now to complete the description of the model, I need to tell you what is the collection of paths on which I impose this probability. In other words, which collection of paths do I sum over to calculate the factor Z? So now there are two natural choices. The first one is the point-to-point that we encountered already. In other words, I fix 2 points on the lattice U and B, and I consider all the paths between U and B. So then Q here would be a probability on the paths between U and B. The other natural choice is the so-called point-to-line, where I fix one of the endpoints, but then I consider all paths of a fixed length that emanate from that point. So all the paths gamma that start at U and with length n. So then Q again would be a probability, a point-to-line probability now on all the paths that start at U and have length n. So I'm going to try to keep these two models side by side for a while here. But before we go on, where did the last passage percolation go? Well, the last passage percolation is what you get when you take the beta to infinity, right? Because if you take beta to infinity, this measure here will concentrate on the paths that maximize the weight. And in particular, if I take log of Z, divide by beta, take beta to infinity, I get back that last passage quantity. So since beta is inverse temperature, this is the sense in which the percolation model is the zero temperature polymer. All right, so the next thing now to do is to record the laws of large numbers for the polymer models. Right? Earlier we looked at the law of large numbers for the last passage value. This line here tells us what we should look at in the polymer model is the logarithm of the Z factor. The Z is called a partition function in the physics literature. So it's the log of the partition function whose limit we want to take, and that's called the free energy in the physics jargon. So let me record those limits next. So limits for a directed polymer, same moment assumption still on the weights. So now I'm going to keep the two cases here, the point-to-line and the point-to-point. Let me add one more feature, one new feature to the point-to-line case. It's convenient to throw in another parameter. We would call it external field. It appears there in the exponent. But otherwise, it's exactly what went before in slightly different notation. And with one other extra feature that makes no difference for anything, but when I sum over paths of length n, as I'm doing here, let me throw in a factor of 2 to the minus n. Just for convenience, it makes the sum into a random walk expectation. That'll be convenient for later. But so otherwise, that's the limiting free energy in the point-to-line case. And then we have the corresponding limit in the point-to-point case. So now the limit is indexed by directions, c, in the first quadrant, and I can just restrict them into this line segment here, because the limit function will be homogeneous, by which I mean that if you have a positive constant inside, you can take it outside. So it's enough to look at this one-dimensional set of possible directions. And so it's again limit of the normalization factor 1 over n, 1 over beta, log of the partition function, and the partition function is the sum over all the paths that begin at the origin and end at n times c. And these limits exist again for subadditivity reasons, just like in the directed percolation case. But let me say a few things about these limiting functions. They're nice functions, again, they're deterministic. This one is pretty obviously convex, Lipschitz. This one is concave. It won't be Lipschitz, it's continuous, but it's going to blow up if you go to the endpoints of this. The derivative will blow up if you go to the endpoints of this segment here. There's a natural duality relation between these two functions, which is the following. And I just want to flash it at you here because I will want to refer to this a little bit later. So this duality will in a sense associate a direction c with a particular value of the external field h. So this identity here is easy enough to prove from the definitions, but it also has an explanation from large deviations theory. So this remark is aimed at those who know what large deviations are about. I don't have time to clarify it any further. But if you look at the large deviations of the position of the endpoint of the path under the quenched polymer measure, fixed beta to be 1 now, on the one hand there is a large deviation principle with this rate function or negative of rate function out here. On the other hand, if I compute the limiting cumulant generating function, I get this quantity here because it's just, this expectation is basically just a ratio of two partition functions. Large deviations law tells us that these two should be convex conjugates of each other, and that's exactly what is being expressed up there. All right. So now the gist will be to ask, can I find formulas for these limits for the polymer? And can I take beta to infinity to get something for the last passage percolation? Now obviously you would want to ask at this point, have we gained anything by going from the percolation, which was a rather simple thing, to this ostensibly more complicated thing, this positive temperature polymer? And we do gain something. If I rewrite this point-to-line limit here a little bit, then an approach suggests itself. So what I did here is I turned the 2 to the minus n into this letter E here, which stands for random walk expectation. So that's this xk here. And I just simply took n as a common factor upstairs. So now this function in parentheses here is an average of sorts. So it's of order 1. And now at least it's kind of clear what needs to be understood in order to understand this limit. The exponential wants to be maximized where this is as large as possible, but those large values may come with very tiny probabilities, so one has to balance the probabilities against the values. And we have a toolkit in probability theory to do this, right? It's called large deviation theory. Large deviation theory has tools for trying to understand asymptotics of exactly this type. And here is a more precise statement. Again, mainly for the benefit of those who are familiar with large deviation theory. So if I'm looking for a variational formula for this quantity here, what I want to do is to derive a large deviation principle under a fixed omega, hence the word quenched, for this empirical measure here. And so what's going on in this empirical measure here? Look, it's keeping track of the environment as seen by the particle. So this capital T here is a shift. is a shift map on the underlying environment space. So this T sub xk of omega is the environment centered at xk, where the particle presently lies. And then I have another component, which is the next step of the walk. And the connection between this and the limit here is that the expression in parentheses is exactly an expectation under this empirical measure. So again, the basic ideas of large deviation theory, for those who are familiar with them now suggest that that's the way to go to try to understand what goes on with this quantity. Now, before I show you a formula, let's do a case where I don't need any fancy mathematics, where linear algebra gives us the answer. So that's the case of a periodic environment. Instead of having IID weights, I'll now take a finite space of periodic environments on the lattice. So here's an example. There are 6 environments here, right, depending on where I put the origin. The letters A, B, C, D, E, F, they just represent the numerical weights attached to the lattice size. So the space omega of weight configurations is now finite, and naturally these translations act there transitively. And I wish now to take advantage of linear algebra, so I want to write my free energy in terms of a matrix. So the matrix I want is this. It's indexed by the environments, and it's sort of an incidence matrix. I put an exponential of the weight at the origin at those pairs omega, omega tilde, where it is the case that omega tilde comes from omega by doing one of these admissible random walk steps in the translation. And now if I can rewrite the free energy in terms of this matrix. So here's the free energy again, and notice that I dropped all the inessential things. I dropped the beta, I dropped the h. It would just obscure the point that I'm making with this and the next slide. So what's going on with this free energy here? As I sum over the paths, I'm multiplying exponentials of weights along admissible paths. Well, that's achieved exactly by raising this matrix here to powers, right? Because there's something in this, at this pair of coordinates exactly when there's an admissible step between them. So this partition function here is exactly the sum of powers of A. A is an irreducible non-negative matrix, so to first order, its high powers are just powers of the spectral radius times some junk coming from the eigenvectors. But we have this 1 over n log in the front, so as we take the limit, all we pick up is the spectral radius. In other words, the Perron-Frobenius eigenvalue of A. So linear algebra gives us the answer in this case. So let me turn it now into a formula that connects with what comes next. So there's the result repeated. The point-to-line free energy is now the log of the Perron-Frobenius eigenvalue for this matrix here. Let me take a textbook characterization of the Perron-Frobenius eigenvalue. So here's the minimax formula. Phi is a positive vector, and this maximum here is really over the row index of the matrix, right? So that's what you can find in the linear algebra textbook. And I want to rewrite it slightly to give me a formula for the free energy. So here it is. I need to put a log in front, so that's what I'm doing here. And I'll use this characterization of the matrix to write it in this manner here as a sum over the 2 admissible steps. And I replaced phi by e to the f. So then this ratio of 2 phi values is a difference of 2 f values in the exponent. And the feature I would like you to just remember out of this for the next few moments is that the infimum is over lattice gradients, right? The infimum is over functions. Well, there's an infimum over f, but what appears in the exponent is a lattice gradient. So now I want to go to the, let me check my time here. A little bit behind, let's speed up. So now I want to go to the infinite dimensional problem. So I need to tell you how to generalize gradients to infinite dimensions. So here we go. This is a notion of cocycles from ergodic theory. It's not a big deal, and the details are not so important in case you haven't seen this before. But it is a function that takes a point of the underlying probability space where the weight slid and 2 lattice points. And I wanted integrable. I wanted to have a certain shift invariance property. So what this here is saying that if I shift the 2 lattice arguments, that's the same as shifting the omega from the underlying probability space. And then the second important thing is this co-cycle property, which says that going from x to y and y to z is the same as going from x to z. So that's a co-cycle. And I'll also want a special case where the mean is 0, so call it centered if that's the case. This is a natural generalization of the gradients, because you can quickly, if you're able to do it quickly in your mind, you realize that a gradient would obviously satisfy these properties, well, if it's L1. But also it goes the other way around, so these co-cycles are exactly what you get if you take the space of these gradients and you close it in L1. So it is the natural infinite dimensional generalization of what we saw before. So now I'm ready to finally give you a formula for the point-to-line free energy. So here we go. Here's the definition again, in terms it's that same limit from a few slides ago. And here's the formula. So it's exactly as it was a moment ago in the finite case, in the periodic case. We have sort of a single step of the Hamiltonian up here, coming from over here. Instead of a gradient, it's now one of these centered co-cycles. And there was a maximum before, which now became an essential supremum under the background environment measure. So I've sort of soft-pedaled this, but there's a probability measure on the background, right, on that environment space under which the weights were IID. And the sum here, how should you think about it? It's really a Markov transition. So underlying this, there is a Markov transition, which in this case is simply the random walk transition that takes either E1 or E2 with probability a half each. And this formula actually is valid much more generally than I have suggested so far. The dimension can be arbitrary. The random walk transition here can be arbitrary. Doesn't have to be directed in particular. And the weights don't have to be IID. But if you want to generalize the IID weights to, say, mixing or ergodic weights, then I have to compensate by making more stringent moment assumptions on the weights. But in principle, this formula is valid in very broad generality. So this is the formula for the positive temperature point-to-line polymer free energy. And now I want to take us back to the percolation model. This was the 0 temperature limit, so now I want to take beta to infinity. Now it's easy, right? One glance at this formula and you see where it's going. If I take beta to infinity, the sum here becomes a maximum, the log and the exponential cancel out. So here it is. So here's point-to-line last passage percolation. Here's the definition of the time constant again from the percolation model, a maximum over weight. And now I put that external field factor there also. And then there's the formula coming from the 0 temperature limit of the previous form. So the log and the exponential went away and the sum became a maximum. All right. Here's a briefest possible slide about sort of history and related stuff. So I've been talking about last passage percolation all along, but there's also, of course, first passage percolation, which where the path geometry is not restricted to directed, and that's been a much more studied model, appeared already in 1965. The origins of last passage percolation, directed last passage percolation, are a little murkier, but it's probably Ross 1981 seminal paper on the hydrodynamic limit of the totally asymmetric simple exclusion process, where a special case of the last passage percolation model appeared, but actually even without the last passage formulation. So, but nevertheless, that should probably be mentioned as the seminal paper. And up to now, no explicit formulas for limits have been known. But then, by a curious coincidence, work was progressing simultaneously in last passage percolation and first passage percolation. So while I was working with my co-authors on last passage percolation, Arjun Krishna, a graduate student at NYU who worked with Surabh Chatterjee and Raghu Varadan, was working on first passage percolation. And he derived a formula for first passage percolation, which is more or less analogous to what we did for last passage percolation, but delightfully our approaches are quite different. So ours is the probabilistic approach that I've outlined so far. His, you relied on recent homogenization results of Hamilton-Jacobi PDEs from Zuganidis and others. Let me maybe add one more comment here. So our original proof for this result is kind of long and technical, but once we have the formula in hand, we actually have a direct proof in just 2 or 3 pages, but we just haven't published that yet. So here's another little recap of these formulas. One for the polymer, and one for last passage percolation. So obviously the next question would be to try to understand something about these formulas. In particular, where would this minimizing co-cycle come from? So there are a couple of situations where we understand it right away. One was that periodic situation that I described already. Another one is the so-called weak disorder situation of the polymer, which means that you're in dimensions 3 and higher and with in high enough temperature. There too, this model is fairly well understood, and in particular we can see immediately where our minimizing co-cycle comes from. But in lower dimensions, the situation is one of the so-called strong disorders, so these models are much more interesting and harder to analyze there. So trying to find a minimizing co-cycle takes me now to this next topic, Boseman functions. Let me first give you a definition. So recall again the last passage percolation value. A Boseman function is this kind of a limit. So what's going on here? Fix points x and y on the lattice. Take a point v to infinity in some particular direction and look at this sort of discrete gradient of the last passage time. If that limit exists, then that's the Boseman function. It's obviously a little bit subtle, right? Because there's no normalization here. So it's serious work to prove that such a limit exists. So as I mentioned in the very beginning of my talk, Chuck Newman brought this idea into probability in the mid-90s when he was interested in the geodesics of first passage percolation. And I can't help but mention this curious coincidence that 20 years ago, he reported on those results at the Zurich ICM. All right. Now, what I want to show you next is how a Boseman function can furnish the minimizer in the variational formula that I just showed you. So here's how it goes. The result we have so far with my co-authors is for the zero temperature case, the last passage percolation. So here's again the variational formula for the limiting point-to-line last passage value. So in order to find this minimizing f, here's what I need to do. I pick the direction c that's dual to h. So just to remind you, this is what it meant. Then I need to make an embarrassing assumption, but at this point there's no way around it. I need to make an assumption about the shape itself, which of course I can't verify, but let me do so anyway. Let me assume that this point C is an exposed point of differentiability of this point-to-point limiting time constant. So what that means is that at C this function is differentiable and it doesn't sit on a line segment where this function is linear. That's the meaning of the term exposed point. But if you grant me this, then everything flows beautifully. There is a Boseman function, an almost sure limit in that direction C. And if I compute the mean of that Boseman function, I get that gradient of the point-to-point limit, whose existence I assumed a moment ago up here. And if I take this Boseman function B and I center it into a centered co-cycle, then I get exactly a function or a co-cycle f that minimizes in this formula here. So the infimum is gone, there's just that particular f. And also the essential supremum goes away. And just this maximum over the direction is left. So in particular, this function here on the right is almost surely constant in omega. And in the theory of homogenization of partial differential equations, when the essential supremum goes away in a variational formula like this, the thing is called a corrector. So I guess we could We could also call this F here a corrector. So this assumption that I needed to make is obviously very unfortunate, but that's the status of this subject now, at this point, for this general last passage percolation. So with that, let me turn to exactly solvable models, where we can say much, much more, of course. So exactly solvable models are these special cases where miracles happen and explicit computations are possible. So now I would have basically two choices for you. I will show you the exactly solvable case for the last passage percolation or for the polymer. So let me do the polymer because that's a newer and perhaps less well known. So that's the so-called log gamma polymer. And here's its definition. I take my weights IID gamma distributed. That's the gamma distribution in case you forgot. And then I define the partition functions as follows. I've changed notation on you a little bit. Instead of putting a sum of weights in an exponential, I'm simply multiplying the reciprocals of the weight across the path. Now, the reason for doing that is simply the fact that it's convenient to keep the weights gamma distributed because when you analyze this model, features of the beta gamma algebra arise very naturally, so things acquire a very pleasant form. Now, what's special about this model? Two features. First is the one that you already saw in Ivan's talk 2 days ago and in Alexei's talk this morning. Namely, there's some deep algebraic structure behind this. So that will be a separate talk, so let me not go there except maybe allude to in passing depending on how far I get here. But there's another feature which is much, much easier and just easier and more accessible. So let me talk about this. There is a stationary version for this process of partition functions. So let me actually construct that so you see what it's like. So now I have two parameters. Rho was the fixed parameter of the IID gamma weights. And there's a second parameter, alpha, that parameterizes these boundary conditions that turn the model into a stationary thing. So just like before, in the bulk, attach some gamma rho weights, IID. And then I put some boundary weights on the axes. And these are convenient to be regarded as edge weights rather than weights on the vertices. And the distributions they take are gamma alpha and gamma rho minus alpha. And now I define partition functions again. So imagine a path that begins from the origin and it ends at a point V. Or imagine all those paths that end at V. Every one of those paths first collects some weight on an axis and then jumps into the bulk and collects some weight in the bulk. So a partition function will have the following form. A sum over all the paths from the origin to V, first collect some weight on one of the boundaries and then some weight in the bulk. And the capital T is the time when the path jumps from the boundary into the bulk. So having put down these weights described up here, I can define all these partition functions. Now where's the stationarity? Here it is. Define all these ratios of partition functions. The superscript alpha now refers to the fact that these are partition functions with the boundaries determined by the parameter alpha. The key fact is that this process of ratio variables is invariant under lattice translations. So if I borrow the cocycle term from earlier, if I take logs, I get another stationary cocycle, and I know the distributions I know the marginal distributions of the variables because of the stationarity. Furthermore, this log of ratios can be obtained as a Boseman function again. So what you should think about here is an analogy with a Markov chain. An invariant distribution for a Markov chain, in a sense, serves two things. It's a boundary condition at time 0 for creating a stationary model, but it's also a limit. And it's the same thing going on here. These log taus, you can think of them as a boundary condition to create a stationary model, but you can also obtain them as limits. So what can we do? Obviously, if you have tractable steady states, one can do calculations. So I'm just going to now quickly flick through some consequences of that one can achieve with these stationary boundaries. So one thing is that we can now compute exactly the limiting point-to-point free energy. So even doing this calculation explicitly is beyond our current understanding for anything but these exactly solvable models. So psi naught here is the so-called di-gamma function, which is the first logarithmic derivative of the good old gamma function. And then the other consequences I wish to mention have to do with these KPZ fluctuations. So you saw KPZ in Ivan's talk, in Alexei's talk. So the features I want to focus on here is the fact that these quantities should have n to the 1/3 fluctuations, and limit distributions come from random matrix theory. So there are sort of two bits of information here, a crude one, which is the exponent, and the refined one, which is the limit distribution. So it turns out that you can access these exponents simply by doing calculations with this stationary model. But if you want the limit distributions, then you need the machinery that Alexei was alluding to and Ivan were alluding to. And that's where the combinatorics would come in. More specifically, by this combinatorial machinery turns probabilities into Fredholm determinants, and once you have Fredholm determinants, you're well set for asymptotic analysis. So let me then finally show you one theorem which can be obtained from this stationary model alone without any deeper combinatorics or asymptotic analysis. Here I'm reminding you of the model once again. Take IID gamma weights, define the partition functions, take the limiting free energy. So KPZ lore says that we should see fluctuation exponent 1/3 for log z. And so here's a result that gives the exponent. So it's a bound of the deviations of log z from the limiting quantity. And well, what I was able to obtain at the time was for moments up to 3/2 minus epsilon, the correct fluctuation exponent. So the way I access this result is by using actually this earlier picture that I showed and coupling together the stationary polymer model with this IID polymer model. I choose the stationary model in a particular way. I pick the parameter alpha just right to make the two as close as possible. I can compute stuff with the stationary model and get some estimates and pass those to the IID model. And of course, let me finish with this point here. Like Alexei indicated, the real open problem is to get true universality. And a great step in that direction, of course, would be to generalize this result to more general distributions on the weights. So I think I'll stop there, and thanks very much for your attention.
So I would like just one question or comment.
Do you really expect the differentiability of the function? I mean, in the homogenization case, it's not differentiable.
Sorry, in what case?
When you homogenize things, I mean, you have differentiability only in some directions.
Yeah, I think
functions are not differentiable, or if they are, that means some rigidity. I mean, it's kind of I mean, why should you expect differentiability?
Yeah, so the question is why to expect differentiability. I guess I don't have a very good justification for why. So if I go back to the oriented percolation, differentiability has been proved in one case. This is work of Tuka Aufinger and Michael Dameron. Let's think of the following situation in last passage percolation. Take Bernoulli weights and say value 1.5, and make the value 1 have high enough probability so that you're above the oriented percolation threshold. Then the shape develops a flat edge in the middle. And what Michael and Tuka proved was that the shape is differentiable at the corner where the flat edge ends. So that's the only case that's known beyond these exactly solvable cases. So I guess what I'm just arriving at is that there doesn't seem to be a good reason to expect that differentiability fails. Since if differentiability were to fail, you might think that that's a good place for it to fail because you have a linear segment and then something else. So I think the general expectation just is that that limiting function, at least in this situation that I was talking about, ought to be differentiable. It's an unsatisfactory answer, I agree, but I think that's all we can say at present.
Okay, so then I will let you use the break time for waiting for the questions or for the comments. So let me now give this present from Owen. Okay, so